Okay, I'd like to start by thanking the organizers for this invitation. Yeah. Okay, so this is the title of my presentation. So it's a fluctuation theorem of entropy production of a partial system in the weak coupling limit. So these different words in different colors are basically these keywords, and I hope it will become clear as I go along. So this has been published here in this paper recently, and then there are some further works under preparation. Okay. So this will be the outline of my talk. So I am going to give a very brief introduction of fluctuation theorem, which is directly relevant for this talk. And so then I'm going to talk about entropy production of a partial system. I'll define what is a partial system. And so what is the question we ask, and then I'll mention some of the earlier studies. And then I'll tell you about our work. And then about our results, and I'll demonstrate this in a model, and then give a general formalism how we get these results, and I'll summarize them. Okay. So let me just give a very brief introduction to this fluctuation theorem. So we know that in thermodynamics of macroscopic bodies, so there is this first law of thermodynamics, which says that so if you add a heat to a system or you work on a system, the net effect is basically it just increases the internal energy of the system, and it essentially defines heat as a energy, and it's the statement of the conservation of energy. But then you soon realize that, okay, this is not enough. Like you realize that, okay, there are some some phenomena you don't see it in nature. For example, although this first law satisfies, one of the textbook example would be like, you not see that this water bottle there is absorbing energy from the environment and jumping by 1 meter. Although by first law, it's possible. So therefore we need the second law of thermodynamics, which essentially says that the things you don't see it in nature, it doesn't happen. This is the statement. So there are several statements of this second law of thermodynamics, and these are equivalent. One of the statements is by Clausius. So it says that heat doesn't flow from a cold reservoir to a hot reservoir if you leave this system as it is. So if you don't do anything. So it also introduced this concept of entropy, and which says that entropy of an isolated system is a non-decreasing function of time. So you always produce entropy, but you cannot reduce entropy of a system. And again, it's a very classical example of entropy production. So it is equality says that, okay, if you are in the equilibrium, basically you don't produce any entropy, and if the system is out of the equilibrium, then it generates entropy. And one of the classic example of this entropy production in non-equilibrium system is that if you have a hot reservoir and a cold reservoir, and you connect them by a thermal conductor, then heat flows from the hot reservoir to the cold reservoirs. And if Q is the amount of heat it flows from the hot reservoir to the cold reservoir, then this is the change of entropy, or it's the production of entropy. So this is the temperature of the hot reservoir, and this is the temperature of the cold reservoir. So in this thermodynamic system, there is no fluctuations, or fluctuations are negligible. Right? So we don't talk about fluctuations. Okay. But this situation becomes different when we go from macroscopic scale to microscopic scale. So where the fluctuation becomes important. So we take the same example. So you have a hot reservoir and a cold reservoir. Now it's a conductor, but imagine that it's like a macroscopic system microscopic size conductor. So again, on the average, heat will flow from the hot reservoir to the cold reservoir. But you will also see fluctuations. Once in a while, you might also see that heat actually is flowing from the cold reservoir to the hot reservoirs. So these quantities like heat flow or work done or entropy, these are these thermodynamic variables. So this becomes stochastic for these microscopic systems. So instead of a well-defined quantity, we have to now talk about the probability distribution of these quantities. So for example, heat, instead of saying that, okay, this Q amount of heat flows, instead of it's like definite quantity, now you will define it by its probability distribution. So here you see that, okay, so on the average, for example, so this is a typical distribution I'm showing. So on the average, although it's positive, but there are contributions you also see on the negative side. And the question people ask in this stochastic thermodynamics is that what is the nature of these fluctuations? So when you go to macroscopic size, basically what happens, this distribution becomes narrower and narrower, and it basically becomes a Dirac delta function. Okay? So it turns out that when is it applicable? So these are some examples where this fluctuation becomes important. So this is the scale basically when your typical energy associated with the system is of the order of kBt. Okay. So these are some examples where this kind of formalism is important. So it turns out that all this entropy, work, heat, etc. can be meaningfully defined in this kind of small system, and there are several nice reviews describing this. One is by Udo, actually, so it's a very nice review. So you can see that actually if you have a system, so like for example, imagine that it's a small system, let's say it's a colloidal particle in water. And so for that, you can define what is the heat absorbed by this colloidal particle, and this is the function. So this eta is the thermal noise by the bath onto this particle, and gamma is the friction coefficient. So this term is basically effective force by this bath times the velocity, and if you integrate it over it, it's basically the energy transfer from the bath to the particle. So this is what you call it heat. So you can define an entropy production, so which is basically this heat divided by this temperature. So this is this entropy production, you call it in the medium because the medium is in equilibrium, and this is this basically entropy loss of the medium. So you can also define a system entropy. So by the similar way you define this Gibbs entropy, like this log of this probability function. So here this probability function you obtain by solving the Fokker-Planck equation for this system. So this is the solution of this thing. So this is a function of these variables which you use to describe the system. But now you evaluate this function along a stochastic trajectory. So you take a variable u. So the argument of this function p is a stochastic variable. So therefore this function is also a stochastic variable. Right? So this is the stochastic entropy of the system you associate with the system. And this function, or whatever this stochastic entropy, it depends on trajectory. So if you take one trajectory, it will have one value. If you take another trajectory, it will have another value. So it's also a trajectory dependent entropy. So it's again a stochastic variable. So now you can add both these two, and then what you call it total entropy. So this becomes the expression for this total entropy. And if your system is in steady state, then what you see is that this P0 is the distribution from which you choose your variable side. It's the initial distribution of the variable. And Pt is the variable at this time t. So if your system is in steady state, the functional form of this P0 and Pt, they are same. So it's the same function. So, and this is essentially the steady state distribution function. So in this case, it can be shown, and it's, I think, quite easy to show that if you take this distribution of this positive entropy production P of delta S total divided by P of minus delta S total is equal to exponential in delta S total. So in fact, it was, so there are a lot of work in this field, and Udo Seifert has shown it's essentially a very nice calculation. It's probably less than 10-line calculation, which you can show that basically this is true for any stochastic systems which satisfies this theorem. So if you define your total entropy production by this way. Okay. So now, so this is the fluctuation theorem for the total entropy production for a stochastic system. So now what I am going to talk about is fluctuation theorem for an entropy production of a partial system. So I'm going to define what is a partial system. So here, all this thing, even here, when we say system, for example, when we say system, what we mean is this particle here. This for example, if it's a colloidal particle, this is my system. I don't call this water molecules in the bath at my system, because there's a time scale separation between this motion of this particle and the motion of the particle in the bath. So this motion of this particle the bath, these are first degrees of freedom. So which essentially gives me a temperature of the friction coefficient, so that I put in it. So when I say a system, the system is the system of slow degrees of freedom. So now, I'm going to talk about this partial entropy production. So imagine again I have this system. So this is this bath. The system is A plus B. They're coupled together by some coupling delta in some dimensionless coupling. So now if I consider this A and B together as a whole, so it's like my complete system. So if I find this total entropy production for this full system, then of course it would satisfy this fluctuation theorem, because this fluctuation theorem, what I have shown before, it's true for any general stochastic system. So on the other hand, suppose I just take, so this is my system, but if I just take only one part of it, let's say A, and I compute the total entropy production defined in a certain way for the system A, so there is no reason to expect that this fluctuation theorem would be satisfied, right? Because it's not the complete system. It may be satisfied, but there's no good reason to a priori expect that this fluctuation theorem would be satisfied for this partial system A. Okay? On the other hand, if this coupling is zero, so then it's like two isolated systems, then you expect that fluctuation theorem would be satisfied for A. Now the question is, if you take this coupling between the system A and B to zero, whether it's same as taking coupling equal to zero. So question is there a deviation of the fluctuation theorem in the limit delta going to zero? As you take coupling constant to zero, whether the fluctuation theorem would be satisfied or not. So that's the question. And in fact, there are similar questions people have asked earlier. So this is a system, this is the experimental system where Udo was also involved. So they looked at this two magnetically coupled particles, and then they look at this entropy production for one particle. And they indeed see that, okay, there's a deviation from the, so this is this fluctuation theorem. If you write it, the same theorem, if you just write it in this log one, different way. So this alpha equal to 1, when you say it's the fluctuation theorem. So they indeed see that, okay, if you put a coupling between these two systems and if you look at a subsystem, it deviates from the usual fluctuation theorem. Okay? So this alpha is not equal to 1. And in fact, not only this, by putting slightly different potential between these two systems, you can also see some other funny behavior. Okay? So it's true that if you have a coupling with some other slow degrees of freedom and you basically observe a part of it, you find deviation from this fluctuation theorem. Okay? But what you see that if you take this coupling to zero, this alpha goes towards 1. So it says that when you, this coupling between this particle and that particle, so when the coupling becomes smaller and smaller, so you recover your fluctuation theorem. Okay? So there are these other studies, there are a lot of other studies, similar thing. I'm not going to go through it. So in all these studies, so they see deviation from the fluctuation theorem when you couple to another system and you just measure part of it. But in all these studies, when you take the coupling constant going to zero, this limit, this becomes equal to the coupling equal to zero limit. So in some other sense, this coupling going to zero limit is a regular perturbation. So if you imagine that you have something and you are doing perturbation theory, so this coupling going to zero is a regular perturbation theory, and when you take coupling goes to zero, it's equal to coupling equal to zero. System size is 1, 0. Like it's a zero-dimensional system, or right? So there's no system size. So now, so what I'm going to present, okay? So it's possible to have certain kind of system. So where this coupling going to zero limit, it becomes a singular perturbation. So it's not a regular perturbation. And in this case, the coupling going to zero limit is different from coupling equal to zero limit. So even in the coupling going to zero limit, you will see deviation from the fluctuation theorem. So I'm going to demonstrate it with a prototypical system, And then I'm going to describe a general formalism by which you can see this kind of fluctuation theorem violation for this partial entropy production. Let me just first demonstrate it. So it's a very simple system. Imagine that you have two colloidal particles. They are connected by a harmonic spring. So this is two Brownian particles connected by a harmonic spring. Okay? So Y is the separation between this particle and K is the spin constant. So you know how to write down the Landsberg equation for this system. So this is the equation for the separation, and this is the equation for the first particle, and this is the equation for the second particle. So this is the force due to the bath, and on top of that we put two external forces, Fa onto particle A and Fb onto particle B. So these etas are thermal noise, so this is basically related by this relation. So now this force, this also we are going to assume to be stochastic. So imagine that we are just putting a stochastic force on this particle A. Okay. So this is the force, and this is the strength of the force, F bar squared. So now we consider two kind of force for this particle B. One is it's completely uncorrelated of the force what you are putting on A. So it's another stochastic force which is just given by this same, but this relative strength between this force A and B is just alpha. So on the other hand, in the second case, we are going to assume force in the particle A and B to be completely correlated, and it's basically the alpha times the force you applied on force B. Okay, so this alpha is one parameter for this model. Similarly, this delta is the coupling strength in terms of this dimensionless variable. So delta going to 0 is basically coupling strength going to 0. And I have another variable theta, which is essentially the strength of this force related to the strength of the noise which is exerted by the bath. Okay. So you can define this entropy production for this system A now. So this is this usual definition, what I have written it before. This is this entropy production for the medium from the point of view of system A plus this term. So this is one way of defining this partial entropy production for the system A. So there is also another way of defining. Suppose imagine you are an experimentalist and you don't know that system B exists, right? So how are you going to define this entropy production? So what usually you do, you take this object because you don't know how to measure, how to get this quantity experimentally. You don't know what is this noise by this thermal bath. So what you do is you replace this quantity by using the Landsberg equation. In the Landsberg equation, this is now the different from this Landsberg equation from this one, because you don't know whether this your particle A is coupled to another particle or not. So you will not put any coupling term in your Landsberg equation. Okay. So and then you just put it back, and this is another way of defining apparent entropy production if you just don't know anything about system B. Okay. So this is, okay, these are these two definitions, and then we were going to look at this entropy production rate where delta S is one of those delta S, and what you see is that it has this large deviation form at large time, and therefore if you take this ratio of P of S by P of minus N and take a log N 1 over T, it will be this IS minus I of minus S. So these are this I of S, the large deviation function. And let's call this function F of S. Okay. So when you say fluctuation theorem is satisfied, it means that F of S is S for all values of S. Right? So that's the, so when F of S is equal to S, that means fluctuation theorem is satisfied. So you want to see now whether we can get anything apart from this. Okay. So let me just tell you the results first. Okay, so these are some, it's kind of like a phase space in this theta alpha plane. So in the limit delta going to 0, you have these regions in this phase space. So this is, for example, if you take this choice 1 for this force B, and you consider this first definition of this entropy production. Similarly, if this one is choice 1, but the second definition of entropy production, and this is for the choice B similarly. So what you see is that there are region, this is this yellow region, where this fluctuation theorem is satisfied. It means that if I compute this f of s, it will be equal to s for all s. But if I go to in any of these other regions in this alpha theta parameter space, this fluctuation theorem is not satisfied. And I'm going to tell you, okay, what are these different regions? Okay, so it will become clear. Yeah. So alpha is the relative, alpha defines the relative strength between force A and force B. And theta is the relative strength between the force A and the temperature, basically, like the heat bath. Okay. So now, okay, to convince you that, okay, what we are computing is correct at least. So this is what we computed, this probability density function theoretically for large time. And we show, you can see that it actually, and then you compare with numerical simulation, and these plots are basically one representative alpha theta values in each of these phase space thing. And you see that it matches perfectly with the theoretical results. Yeah. Delta is the other axis, right? So if you look at theta, alpha, delta, there's another axis, and this is the axis when delta going to 0, right? So this is the third axis, delta equal to. Okay. So now, okay, so this is the probability density function, and you see that actually it matches nicely with simulation. So you can also compute this large deviation function, and you see that, so these are the large deviation function. So no. So there are 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So I took 1 point representative point from each region, and these 9 are basically these 9 plots from one from each region. So now you can also, given this probability density function, you can also compute this large deviation function, right? So essentially you compute this large deviation function for very small delta. So you actually put a value of delta and you compute it. And you also compute it in the limit delta going to 0. And you see that your theoretical result, delta going to 0 result, and this, when you take delta smaller and smaller, it actually converges to delta going to 0 limit. So whatever answer we are getting from the computation of delta going to 0 limit is correct. So that's what this graph says. So for example, this one, like you can see this red one is from delta equal to 0.1, it's far away from there, but by the time you go to delta equal to 0.01, you can't distinguish from this green one, right? So it's already at this delta. Okay. So now we want to see, we have this large deviation function. So whether, if we compute this function I of s and minus I of minus s, whether it will be a straight line or something else, right? So this is this plot. So again, so these two plots, right? So these two represent these points where these yellow regions, so where this is exactly a straight line. But you see that all these other regions, it's not a straight line, right? It says that in all these other regions, fluctuation theorem is not satisfied in the limit delta going to 0. Okay. So one can also compute this, actually this asymptotic form of this function, and these are given by these lines. And you see that your whatever you compute this large deviation function you compute, and then you actually match with this your asymptotic result, and it actually matches these asymptotic results very nicely, right? So these green lines are basically, these green lines plots fs equal to s. And you see that this line, for example, is very different from fs equal to s line. So it says that, so I have convinced you probably that with this demonstration that it's possible to have violation of fluctuation theorem even in the limit delta going to 0. And now I'm going to say what is this mechanism by which it can be violated. Okay? Yeah. Delta going to 0, right? That's the whole point of this talk. Delta going to 0 is not equal to delta equal to 0. Yeah. Yeah. So that's why this, so delta arrow 0, right? This is delta going to 0. So I hope it's clear that the whole point of the talk is to delta going to 0 limit is different from delta equal to 0 limit. Okay. So now, okay, so it's actually, I find it quite nice. It just comes of a very nice mathematical analysis, and I'm going to show you actually how it can happen in certain kind of system. It's not quite general, but in certain kind of systems, it can happen. Okay, so how do you compute? Usually, you have to compute this entropy production. Let's say this is the entropy production of the medium, and you have to compute its distribution. So usually what you do is that you compute this generating function, and this generating function satisfies some kind of Fokker-Planck-like equation. And for large time, what you can do is you can expand this solution in terms of the eigenbasis of this Fokker-Planck-like equation operator, right? So it has discrete eigenspectrum, and you expand there. And at large time, this object is dominated by the term having the largest eigenvalue. Okay. So now your total entropy production is this guy plus this guy, but this is something like a boundary term, right? This is just depends on the variable at the initial time and the final time. So therefore, if you also compute the generating function of this entropy production, it will have a similar behavior, right? So this dominant part is still exponential in t times mu lambda. So if you look at this time average entropy production, so how do? You just do a saddle point, you just invert this, and you just do a saddle point calculation to invert this. Right? So this I of s is nothing but this largest part of this thing, and which you get by this maximizing function. Okay, so this lambda is your saddle point basically. So now, when you say that fluctuation theorem is satisfied, for example, delta equal to 0 case, you know that fluctuation theorem is satisfied. So it means that this large deviation function must have this symmetry, right? That's this is another definition of the fluctuation theorem. So now it also means that it's very easy to show that if this symmetry is satisfied, your mu lambdas must also satisfy some other symmetry, which is usually known as the Galois-Cohen symmetry. So not only mu lambda, your this saddle point also has to satisfy another symmetry, which says that, okay, lambda 0 of s plus lambda 0 minus s equal to 1. Okay. It's essentially like this, you can call it Galois-Cohen symmetry. Okay. So now, imagine a situation where your mu lambda, so mu lambda, look at as a function of lambda on the real lambda line. So the analytic part of the mu lambda is bounded by, so basically there are two singularities at lambda minus and lambda plus. And so what you have is now this mu lambda lies here. I mean, this outside is also there. But when you now compute the saddle point will always lie between lambda minus and lambda plus. So if your mu lambda has some kind of, let's say, branch points. There's a branch point at lambda minus and lambda plus. Okay. So again, you can show that, okay, so this is like the branch point behavior. When lambda goes to lambda plus, it has this behavior, and lambda goes to lambda minus, it has this behavior. So again, these two they have to be same because of Galois-Cohen symmetry. And as I said that, okay, if you compute this, if you take this one and compute the saddle point, so you see that the saddle point basically lies between that. So when your s goes to plus infinity, what happens? The saddle point goes and hits lambda minus. Similarly, when s goes to minus infinity, saddle point goes and hits this lambda plus. So this is what I have shown you here. So now, when you compute this I of s, it's just this guy. So the leading order, therefore, it's this object computing at lambda plus and lambda minus, depending on whether s goes to plus infinity or s goes to minus infinity, plus this term, plus higher order terms. So those terms will be 1 over s to the power something. Okay. So now, if you compute this I of s and I of minus s, so it's what you see is that, okay, these two are same, so they cancel. So then it's lambda plus plus lambda minus. And then, I think one should be negative actually, okay? This should be negative. And then you have subleading terms. So now you know that this lambda plus plus lambda minus is equal to 1, because that's, I have shown you before. So, and if the fluctuation theorem is satisfied, so in this case, what happens? All the subleading terms actually becomes exactly equal to 0. So this subleading term from here, it cancelled by subleading term from here. So in this case, therefore, this you see that this I of S and minus I of minus S is linear in S without anything in front. So now what happens when you have a non-zero coupling? So imagine that you again have these two branch points, right? So you know what is the behavior now because we have computed there is a similar procedure. So now if you compute I of S minus I of minus S, so you have this behavior. So in this case, there is no reason that this term has to be 0, right? Which was 0 in this case, where this is equal to this. So in general, there is no reason that this term has to be 0. There is no reason that this guy has to be unity. Okay? So therefore, if you take for any general delta, this will not be satisfied. So what you see is you see something like that. Okay. So this is the case delta equal to 0 case. And if delta is not equal to 0, some finite delta, so at least what you'll see that for large S, you'll see a different slope, so which is essentially this one. Now this question is what happens when you take delta going to 0, whether this slope becomes 1 or it stays something away from 1. So what we are saying is that, so there is possible that, so these are the 4 possibilities, right? So you have this lambda plus minus this thing, so you have these 2 branch points. Whether those branch points, basically when you take delta going to 0, it merges to the original branch point, what is delta equal to 0 case, or becomes something else. So what you see is that delta going to 0, it's possible that they goes to the same one. This is, I call it P1, possibility 1. So in this case, it is satisfied. But there are also other possibility from general ground. You said, okay, I mean, like one guy goes to the, so let me just maybe, so I had this lambda minus and lambda plus, which correspond to delta equal to 0 case. And let's say I have some other branch point, which is lambda minus delta and lambda plus delta. The question is whether if I take delta going to 0, this branch point goes and merges with this branch point. Similarly, whether this goes and merges with these points, or this has some goes and gets fixed at some other points. Right? So this first possibility is that one where basically they go and merge to this, and there are these other possibilities where one guy can go and merge with this, but not the other guy, and vice versa. So in this, all these other 3 cases, basically what you see is that your fluctuation theorem is not satisfied. Okay. So how do you see that? So suppose this guy doesn't go and merge with this guy, right? So let's say that's case 2. So now, if I look at this mu lambda again around this point, so what you see is that you have a part which I call it like an analytic, in the sense that if you take this delta going to 0 limit, that's the same as mu 0 lambda which we have before. But there is another part, which is this singular part, which is lambda minus, which is another branch point, with a prefactor which is delta to the power beta. So now you see that if you take delta equal to 0 exactly, this term is not there, right? But now you have to see what happens when you take delta going to 0 limit. So how does it, delta going to 0 limit is different from delta equal to 0 limit. So you see, so this is already I'm taking delta going to 0 limits, I'm just keeping the leading term. So now in this limit, if I compute the saddle point equation, so it becomes this one. Right? So this is just the saddle point equation is nothing but mu prime lambda star is minus s, and mu I have divided into 2 parts. So this is what it becomes. So now if your saddle point is very far from this branch point, in the limit delta going to 0, this term is negligible. Right? So I can throw away this term, and what I find is that I have this old large deviation function, because this large deviation function is just given by my now mu 0 lambda star is equal to minus s. So this is the same large division function I have computed. But on the other hand, what happened now, I'm changing s, right? So at some point what happened is your lambda star becomes close to this branch point. So at that point, you can't throw away this term. In fact, this term becomes dominant compared to this term. So now you have to compute a different saddle point equation, right? So now if you compute this guy, taking account to the second and this one, so what you get is that you get something else. In the limit delta going to 0, it will give you something else. Okay? And this is what you see, in fact, and this is basically responsible for this deviation for this fluctuation theorem in what you have observed. Okay. So, okay, these are this, you can call it a new fluctuation theorem or whatever you want. Basically, it's saying that, okay, it's what you can see in the limit delta going to 0 limit for this kind of systems, you can see this f of s, which is different from s, and these asymptotics are basically given by that depending on all these 4 situations. No. See, beta, see, this is, what is this beta? Beta is, you're just expanding to the lowest order, right? Beta can be 1, or if there's a singular behavior in delta, it can be like, okay, fractional, but it's usually we expect that beta to be 1. But it's some number basically. 1, 2, half, 3 by 2 doesn't matter. Some number, right? Some small number. Order 1 number. No. You cannot. See, there's a denominator, there's a numerator. However small that numerator is, you fix it. Whatever beta you choose, delta you choose, is a fixed number. 10 to the power minus 5 is a fixed number, right? So now you can take this lambda star, becomes smaller and smaller to this delta, right? So at some point, this gap will become smaller than that number, right? Because that's a fixed number, whatever delta to the power beta, whatever delta and beta you choose, right? So now, okay, so let me just summarize it now. So in summary, what we have shown that, okay, it's possible to have a violation of fluctuation theorem by driving the system in a certain way, even in the limit coupling strength going to 0. And okay, so you can call it some new relation or something. Basically, say another way of looking at this fluctuation theorem when you drive the system stochastically. And okay, one can think of it also a way of finding if you have some system, you want to find out whether it's coupled to any other system or not. You don't know. You can just apply this stochastic force on this system and see whether fluctuation theorem is satisfied or not for large time. And if it is not satisfied, then you think that, okay, you might be coupled to any other systems. Okay, yeah, so I guess I'll just stop here. And if there is any question.
Sanjib, this is really very intriguing work. And you've shown us a nice mathematical analysis of the underlying structure. But additionally, it would be good to understand the physics.
Yeah. So
and one aspect is that sometimes, as you know from earlier work from Cohen and Van Zoon, that if you use harmonic internal energy, things can become strange. So have you checked that, or does it depend crucially on this assumption of a harmonic coupling? That would be my first question.
Okay.
And the second question would, have you checked, or can you get it also in discrete networks like the one Debashish was talking about earlier?
Yeah, okay. So yeah, it's a very nice question, a very good question. See, of course, the problem is that only in the harmonic cases you can do calculations. But okay, let me just give you a physical argument why this kind of thing might happen, and you might expect to see it in other cases. So why are you seeing this? So because we have these two particles, right? So imagine that you have this one particle. It's a free particle. So if you have a free particle, there's no time scale associated with a particle. Suppose you have just one Brownian particle in water. There's no time scale of relaxation for this particle. So now, once you have this coupling, it introduces some kind of time scale. So for example, let's just give me a simple example. If you have a Brownian particle, two Brownian particle, and you just measure the variance of one particle, variance in the displacement of one particle. So initially what you will see is that it goes like 2 dt because it's like a free particle. But at some point coupling will be important, and last time you will actually see that, okay, there's a center of mass motion, and you'll see deviation from this 2 dt. So what this coupling does is essentially introduces a time scale. And I think if you look at beyond that time scale, this system is no longer becomes like a weak coupling, this thing. So it becomes like a strong coupling system. So I don't know whether it's only with harmonics I mean, I would imagine that if you take any other potential between these two, this thing, bounded, yeah, bound, no, let's for the time being, let's say u to the x to the power 4. Yeah, but if you have a bounded potential, I think then, I mean, there's still a time scale associated with that, but I do not know. I mean, in some sense, there's still a time, if you can associate a time scale with that, then you get something distinct. So you can actually verify this one. So if you, I mean, so this is what I was saying that, okay, this small example says that, okay, you can see violation of thing if when this relaxation time becomes important. It doesn't explain fully because even there we see that some parameter range where this fluctuation theorem is satisfied. Yeah. But what we can say is that if you just put this thing in a harmonic trap, because what happens if the system is in a harmonic trap, there's already a time scale there. So now what happens? So this time scale is, let's say, this tau k0. So this k0 is the stiffness of this trap. So now you introduce this coupling. So that coupling only modifies this existing time scale by a small amount. So now if you take this coupling going to zero limit, it essentially goes to this coupling. So in this case, it becomes a regular perturbation. So, but I guess this is true with any potential I would imagine, but I can't, because I don't know how to compute that thing. But, and numerically, it's very, I mean, it's not so easy to see because you have to also go to a larger and larger time scale to find these things. Also, yeah, discrete, I do not know again. Yeah, so.
Sanjib, here. So, did you show that there is a regime in the phase space in which the fluctuation theorem symmetry is actually conserved?
Yes.
And what is this regime and why is it conserved in that regime?
Don't ask me why, because I don't understand. I mean, I know that this is the regime where this, I mean, I understand mathematically why it is happening. So actually it's very...
Has it anything to do with the time scales you are talking about now?
So that's what I'm saying, that I just gave you a physical argument. Sometimes it's very easy to take a physical argument and say, oh, this is very simple. It must be explained everything by that. So it's, although it's, this time scale associated with that, but it doesn't explain everything. So let me actually give you another plot. Actually, it explains at least some of this thing, and at least mathematically. Okay. So what is happening is that, okay, you are looking at this mu of lambda. This is your that largest eigenvalue. Okay. So it has this kind of form, and you are looking at where this guy has some singularities. So you are looking for branch point of this guy. So when do you have a branch point of this guy? So basically when this guy becomes 0, right? So then this guy becomes log of negative number becomes imaginary. So that's when you expect branch point to happen. So what do you have? Basically, if this guy has this kind of form, and if you plot this lambda plus and lambda minus for each u, because it now depends on u. For each u, there will be a lambda at which this guy becomes 0. Actually, there are 2 points because it has a quadratic form, this guy. So it has 2 points when this guy becomes 0. So now if you actually plot this thing as a function of u, this lambda plus and lambda minus, so this dashed line is the line with delta equal to 0 case, and this red line is delta going to 0 case. So what happens? It more or less follows this guy, and then it goes there. So now when you look at the lambda plus, so you're basically looking at the values of lambda when this thing becomes imaginary. And that's the, if you're looking from this side, you're looking from the minimum of these values, right? So all these values, for all these lambdas, this guy becomes imaginary. So you're looking at this minimum where this is. So this is this minimum. So this becomes your lambda plus whatever this is. But there's another situation where this doesn't happen. So it's again more or less like that. But instead of going down, it goes up. So in this case, if you take delta going to 0 limit, it basically, so that guy is irrelevant because that's higher. So it essentially gets stuck with this one. So that's your old lambda minus. So if your both the guys goes to this one, so your fluctuation theorem is satisfied. But if one of these thing happens, it's not satisfied. So this is something I understand mathematically, but trying to put a physics why exactly it happens, I have very little clue. Let me just say that.
Sanjay, one question. You didn't show the plot of your function I. So this large division function has one minimum, or does it have more than one? For example, if it has a sort of metastable kind of thing, and in the limit delta going to 0, can it then sort of touch 0?
No, it doesn't have first order singularities. That's what you mean. Yeah. So this is the large division function, like that basically. So I don't have this minus sign.
So let's say you do an experiment where you see the violation of the fluctuation relation.
Yeah.
Okay. And so you know there are some hidden degrees of freedom. Yeah. Is it possible to also tell what, is it possible to get a cue about what these hidden degrees of freedom might be by playing with the FATs and FBTs, or?
It's like asking that, I mean, like if I measure the temperature here, do I know where all the molecules are? I mean, like, no, I mean,
so you can't comment about.
Yeah, I mean, it's very difficult to do it from one measurement, like, because there might be some other coupling also, right? So I don't know what kind of couplings are there. So I can only say that, okay, there's some coupling with this. There's some other hidden degrees of freedom with which it's coupled to. But I would not know. Because, I mean, like, you're getting more from just small thing, right?
I had a question. So in your two definitions of entropy production, so the contribution of the second part.
So that's
there. I mean, the P steady state. Why is it different? Like experimentally, what you measure?
No, what I'm saying is that, see, actually that part is that whatever this part is not very. So you're saying these two, right?
Why are they different?
So I'm saying, okay, this is first of all, this is not very important for this calculation. But why is it different in the sense that, okay. See, in the first one, you have actually solved this whole equation, full equation, right? And then integrate out B degrees of freedom, right? But it will still have this K, I guess, right, in this formula.
Yeah, but the steady state, like if you look at the marginal of the steady state of A,
yeah,
that should be the same as what you measure in experiment, right? And like experimentally, if you somehow figure out the steady state distribution.
But no, if you measure the steady state, then it will be same as that one.
Right, yeah.
But so I'm saying that now, so now you can do two things in this experiment. You actually measure the this thing, and then you take as this thing. So there can be a third definition where you put this thing and put that one. So what I'm saying is somehow, suppose in experiment you guess the system and model by this equation, then it will be there. But this part is not very important because it just contribute to the subleading terms actually. So
it's almost similar to Rajesh's question. Is in experiments, why do you see sometimes fluctuation theorems to hold? Because you would always have some degrees of freedom which you have not counted for.
So one of the reason might be most of the time in experiments, I'm not saying all the time, but you put the system in some confined potential trap or something like that. So and if you put this thing in a trap, usually what happens if the coupling is weak, that it will not show up. Okay, it doesn't. Yeah, this one. So most of the time, I think when you do an experiment, you put thing in a confining potential. And if you put in a confining potential, even here you see that if you take this coupling is very weak, so it will be essentially like coupling equal to 0 case. But this, whatever this example I have given, it's in principle do it in experiment because it's just two Brownian particle and you couple by some, I don't know, some kind of harmonic. I don't know how you do, but it's possible to do in experiment. I actually see that, okay, Paul, it's a deviation from the fluctuation theorem in this case. It's like if you look at a free system, basically.
We need to stop now. So let's thank Sanjib again and